Hello everyone, hope you're doing well. Today I want to look at some momentum questions, specifically dealing with collisions in 2D. So usually the introduction to momentum will start with 1D collisions, and in this video I want to go to the next step, the next level, and look at two-dimensional problems. Now the most important thing with momentum questions is understanding the conservation of momentum. Usually we're going to be dealing with elastic collisions, inelastic, or completely inelastic collisions. And regardless of the type of collision we're looking at, momentum will always be conserved. And that's the most important part for the two questions that I will be working on today. So let's jump right into the first one. We have two horrendous drawings of cars, and I apologize for that. I was never an artist. But anyways, we have one car that weighs 500 kilos going 40 kilometers per hour east, and we have another car that also weighs 500 kilos going 20 kilometers an hour south. And we're given a bit more info here. If this collision is completely inelastic, what is the post-collision velocity for the two cars? Okay, it is completely inelastic, and what that means is post-collision, my masses are actually going to stick together. Meaning, I only need to solve for one post-collision velocity. So what do I mean by masses sticking together? Well, the two cars are going to hit each other. Let's say they hit each other right around here. And then post-collision, they're going to have a combined velocity at some set angle. So our job is to figure out what is this vector right here, assuming mass 1 and mass 2 are combined. Now, when we're thinking of momentum in 2D, we want to break down momentum in our x dimension and in our y dimension. So let's look at x first. The only momentum I have pre-collision in the x direction will be from this car because we're moving east. So let's plug in our values. Momentum is mass times velocity, so this would be 500 kilos times 40 kilometers an hour. Like I said, we do have a mass here, but we have 0 x velocity. We only have y velocity, right? So we can ignore this section. And we're going to set our pre-collision momentum equal to our post-collision momentum, and that is due to the conservation of momentum. So this will be our post-collision momentum. And as I mentioned before, it's completely inelastic, so our masses will be added together. And so we have a final velocity in the x dimension. Let's set things up for y now. In this case, our car here moving east will not give us any y momentum. So we have a 500, but this time we have a 0 here, so we can ignore that. And here we do have some y momentum. It's going to be 500 kilos times 20 kilometers an hour. However, I need to think of how I'm representing direction. Usually north will be positive and south will be negative. So since we're going 20 kilometers an hour south, I will set this as a negative number. And same deal here. Okay, we can also just add the mass values here as well. It'll just be the two cars stuck together. So let's just solve all of this multiplication here. 500 times 40 will give us 20,000. We ignore this. And on our right side, we get 1,000 VF, specifically VFX, right? Our final velocity in the X dimension. For our Y equation, we're going to look at our values here. 500 times negative 20 gives us negative 10,000. And we also have 1,000 VF Y. All we got to do now is isolate for our variables. So in our first equation, we want to isolate for VFX. I'm going to divide 1,000 out onto both sides. And VFX equals 20 kilometers an hour. Going to do the same thing for Y. And we get a negative 10 kilometers per hour. And the negative just refers to our direction. So east will be for our first velocity because I set the original velocity of this car as a positive 40, meaning the east direction is my positive direction x-wise. So all of this looks good, but these are just the components of our velocity. We still need to add them together. So let's do that down here. Usually when I add vectors together, I do tip to tail. So let's take VFX, which is 20 kilometers per hour this way, and then VFY, which is 10 kilometers per hour this way. I can do that a little bit better. There we go. So we have our right angle triangle. We have the magnitude of our velocity to solve for, and that will be the hypotenuse. And we also have the angle because velocity is a vector, so we need a direction. Let's look at the magnitude first. Just simple Pythagorean theorem. I mean, I could leave this negative, but it won't really matter because we're going to square the number and we'll get rid of that, but I'll leave it negative. So we get 100 plus 400 gives us 500, and then I need to square root both sides. And this will be roughly 22.36 kilometers per hour. Finally, we need our angle. I can see we have our opposite and our adjacent side. I could use the hypotenuse since I already solved for it, but let's just stick with opposite and adjacent, meaning we need to use our tan ratio. And to isolate for this angle, I just need to inverse tan our right side. And I'm going to get a value of roughly 26.57 degrees. But our value is technically negative, and the reason why it's negative is because it's referencing east 26.57 degrees south. So if I wanted to specify my answer, I would say the post-collision velocity is 22.36 kilometers an hour, east 26.57 degrees south. So we are going downwards on our angle. Okay, hopefully that was pretty easy to follow along with. Now I want to move on to a different kind of collision. Let's move on to the right. We have some more horrible drawings for you. This time we are dealing with a normal inelastic collision, not completely inelastic. So our objects are not going to stick together post-collision. However, we still can't use our energy equations because the only time we can use energy in a momentum question is when we have a completely elastic collision. And that means that energy will be conserved. But that's not the case in this scenario. And since I'm Canadian, I'm using curling stones for this example. So my curling stone is yellow. My opponent's is in red. So in this scenario, I am throwing my stone, which weighs 5 kilos, at 3 meters per second. And I'm going to hit my opponent's stone, which is also 5 kilos, and it's at rest. And my goal here was to move the opponent's stone upwards. So you can see post-collision, the red stone is going upwards at a 30-degree angle. Meanwhile, my stone goes downwards at a 15-degree angle. And with this information, we can actually figure out the magnitude of both post-collision velocities. But there's going to be a few more steps involved. First, let's look in the x direction. Difference here is that our masses will continue to be separate. And all I've done with the subscripts here is this will be velocity of our first object, and that's mine. And it's in the x dimension, and it's my final velocity. For this one, it's the second object's velocity, number 2. Also in the x dimension, also its final velocity. So let's see what we can plug in here. I definitely have x momentum from my first object. So I have 5 kilos, and this time we're measuring speed in meters per second. That's fine. I also have 5 kilos here, but our object is at rest, so we can ignore that. And then post-collision, mass is the same, so we'll leave it at that. And I am going to do something with these variables, but first I want to set up my y equation. All right, in the y dimension, we do not have any starting momentum, right? Because our first object is traveling east and our second object isn't moving at all. So this whole side will be set to 0. On our right side, which is post-collision, again, we have the same masses, so that's fine. And we have y velocity. Now, the trick for this kind of question is we're going to want to isolate for one variable in one of our equations and plug it in to the other one, and that way we can solve for one of our variables. However, you may notice that the variables between these two equations are not identical. So if I compare v1xf to v1yf, those are not the same. We're talking about 2 different dimensions. What I need to do is try to make these 2 equations share common variables. And the way I can do that is by representing the x velocity with respect to the overall velocity. So these are two triangles that I'm going to use to help me out. And all they're doing is referencing the post-collision angles of my objects. So this down here is actually object 1, because that's the yellow stone going downwards. I'll draw an arrow to show that. And this here will be object 2, because we're going upwards, and that's the red stone. Probably should have put number 1 up here and number 2 down here, but oh well. Let's see how we can represent this with the overall velocity. So this is my x component on both of them, and this is my y component. So for the first object, if I wanted to reference my x velocity, I could go cos 15 equals x, or vx, over the overall final velocity. And if I move this over here, I will get vf, which is my final velocity, cos 15 equals vx. And this is probably the most important part of this kind of question. So let's get a bit more space down here. So what I can do is I can actually rewrite these two equations using cos in the x dimension and sine in the y dimension. So let me show you how I would do it with sine using the same object. If I said sine 15 degrees equals negative y over overall final velocity, move this over here again, and I've got another way to represent Vy with respect to Vf. And actually I want to move the negative here as well. That looks better. So using this trick, I'm going to rewrite these two equations. And let's see how that looks. All right, let's get to it. 5 times 3 equals 5 times V1F cos 15 plus 5 times V2F cos 30. And these sections here are just new representations for our x velocity. I'll also do the same for y, so we actually have 0 on this side, and we're going to do 5 negative v1f sine 15 plus 5 times v2f sine 30. And notice how this part here is not negative, because for our second object, y is up in our positive direction. Okay, I can simplify this by removing mass, right? Because the mass of my first and my second object are the same. So I could technically factor out the 5 on both of these equations, and that will just keep things a little bit cleaner. And I also want to get a real number from these cos and sine values, because these are just numbers. So keep scrolling down. Let's do x. we've got 3 equals 0.966 v1f plus 0.866 v2f. And I will do the same for y. Okay, looking a lot better. Now we're sharing similar variables, or the same variables actually, between our two equations. Now we just need to isolate for one of our variables in one of our equations. I'm going to pick y to work with, and I want to isolate for v2f. So I need to move this over to my left side, and we're going to get 0.259 equals half of v2f. Still, we need to isolate for this variable. So let's divide both sides by 0.5. And this is the value I get for v2f. Now all I need to do is plug this in my first equation, my x equation. That way I'll only have one variable to solve for, which will be v1f. So this is the x momentum. And multiplying those two numbers out will give us and finally, we just need to collect our like terms. So that will be 1.415. Divide our number out. And v1f is approximately 2.12 meters per second. So we solved for one velocity. The way we would solve for our second velocity is just by plugging in 2.12 into either equation and figuring out what v2f is. So you can try that on your own. I know just from doing the rest of this problem that the second velocity will be, let me check my notes, roughly 1.1 meters per second. So our yellow stone is going at 2.12 meters per second, east 15 degrees south, and our red stone is going 1.1 meters per second, east 30 degrees north. Okay, that was a lot to cover. Two very different kinds of questions because they're two different kinds of collisions. But hopefully you found this helpful, and with this information, you can solve quite a few different kinds of momentum questions. Thanks for watching, and have a great day.